Hi linear algebra students. So in this video we're going to prove the Pythagorean theorem. So you know what the Pythagorean theorem is. However, in this scenario we're using it on vectors and we're using the concept of orthogonality. Okay? Orthogonality is another way of saying perpendicular. We define that by the dot product of two vectors being equal to 0. And we need to show that this is what it means, that it is perpendicular. And a nice way of doing it is actually with the Pythagorean theorem. So this is the theorem. We are given u and v vectors in our n. Then the norm of u plus v squared is equal the norm of u squared plus the norm of v squared if and only if u and v are orthogonal. Okay, so you have the sketch right over here. This is u, this is v, this is u plus v. Okay, so it is like whenever the vectors u and v are orthogonal, well, you get the familiar triangle that you are used to. Okay. Now, how do we prove this? The idea is to write this as being the dot product of u plus v with itself. So you're gonna write u plus v squared, and you're gonna write u plus v dot u plus v. Okay? And this calculation, you will repeat it very often. And the properties of the dot product allows you to basically expand as if it was kind of two factors. Okay? So in other words, what we get out of this is that we'll get u dot u. Okay, I will not go super fast, but faster than in my last video, just because you should be used to that. So it's u dot u, like plus u dot v. So plus u dot v plus v dot u plus v dot v. So here, remember, I'm using both left and right distributivity at the same time. So left and right distributivity. Okay. Well, the next property that I'm going to use is commutativity. Okay, so in other words, the fact that these two things commute makes it so that, so this is commutativity, okay? It means that these two combine to give you 2 times u dot v. And by the way, let's actually say, okay, well, u dot u is u squared plus 2u dot v, okay, plus v squared, okay? So, by the way, this is true for every vector, regardless of if they are orthogonal or not. And this is what will allow us to prove the theorem. So, first of all, let's prove this way, like this way right here. In other words, we prove that the if statement, right, is that this is true if this is true. So if u and v are orthogonal, so u dot v, okay, are orthogonal, means that u dot v equals to 0. And so this means that actually I will color code this in green, okay, just to show you what happens. Oh shoot, this is not a vector. This is just a, I messed up over here. This is just a number, all right? Keep that in mind. So, okay, here what we have that u plus v squared. So I'm using the equation that I have over here. This is going to be u squared plus 2 times 0. So yeah, let's just say 0 here. I don't really care. Plus v squared. So this is QED for this little part right here, okay? So I'll put it QED for this side, okay? But the other side is proved very similarly, okay? So let's actually erase the theorem itself. Okay. So now suppose that so if u plus v squared, let's actually color code this in black now. Let's suppose now that u plus v squared is equal to u squared plus v squared. Then in this case, what I can do is I can replace this side in this equation. So it means that what I have is u squared plus v squared, okay, is equal to this, is equal to u squared plus 2u dot v plus v squared. And from there, what you should see is that, again, these cancel. And actually, I will respect my color code here. So the v squares cancels. And the u squares also cancel. Which means that you are left with 0 is equal to 2u dot v. And of course, dividing that by 2, you get that u dot v equals 0. Which means QED for the only if part. All right, I hope that helps. See you in the next video.